Okay, so let me continue from the previous lecture. So hopefully there's a bit of time to think over these questions. I actually add another one during the break. But let's just start from the first question that I raised about benchmarking and certification. So yeah, how many measurements do we need in order to check if rho is close to psi? What is the best one could come up with? So feel free to raise your hand if you have some thoughts. Yeah, you mean like in order to check whether it's epsilon close, we only need order 1 over epsilon squared measurements in order to do so. How are you thinking about this?
It's from the theorem for
right, because one can just pick m to be equal to 1. There's only one observable, and that observable.
Yeah, just like its station value.
Of psi. Yes. That's great. So that is very easy to answer. And note that restricting to Clifford gates doesn't really change. Naively, we would just measure psi, but then using that theorem, we can just use Clifford gates. So
that's not an answer, but I thought it was funny because m is 1 and log 1 is 0, so yeah.
Yeah, so because it's big O notation, so there's always some constant factor.
But it's 0, log.
No. I mean, like, big O notation means when I write order log m, it's always order log m plus some constant. So there are some constant. Okay. So yeah, and did people have time to think about the second one? If that's also easy. Go ahead.
But it should be like log h.
Yeah, log h over epsilon squared. So that's right. And what about the new question that I added? So the question is the following. So now we consider essentially a space. Like now it's not just h of them, but there's a hypothesis class, a family of hypotheses, such that the hypothesis is basically we assume that the state can be generated by, at most, capital G gates. So think about it as we wanted to do tomography. So here, this is a full tomography case. We wanted to fully learn the state, but we have an additional promise that the state of interest is of bounded complexity. So in general, a state rho requires exponential number of measurements to create. But what if now we have the additional assumption that it only requires a bounded number of gates? So think of capital G as a parameter. Maybe it's scaling linearly in system size or polynomially in system size. Then how many measurements is required to perform tomography in this setting? Again, feel free to think about it and just raise your hand if you have some thoughts on this question. It should also be quite obvious from these two. It's just a slightly more advanced version. Okay. So what's the answer for that question?
I don't know if I'm oversimplifying it, but just same answer as for the previous question, log g times 1 over epsilon squared.
What is your reasoning behind this?
Yeah, so you apply these g different gates to the factorized state, to the product state, and you just see which of those you're closest to, which of those resulting states you're closest to.
So that's the algorithmic idea is correct, but I think counting-wise there's a bit off. So did anyone wants to add on to what's the right count? Basically, there's a relation between h and g. H is not linearly in g. It's bigger.
Actually, I have a question on that question. So,
Yeah.
are we fixed the architecture of the circuit, and do we have some kind of gate sets, for example?
So for simplicity, I mean, it can be pretty general. It can have arbitrary architecture, and G gates. The gates can be arbitrary 2-qubit gate. But for now, for this one, I think one can start by thinking about the simplest case, which is, say, this is a fixed architecture. So what is the connectivity? It's all fixed. It's just that for each of the 2-qubit gate, there's freedom in choosing them. And furthermore, for now, let's assume it's a discrete gate set, so like a Clifford plus T gate set.
Then it might be linear in terms of G, I guess.
Yes. So basically, that's correct. So in this simplest ground, it would be the answer to this would be how many measurements do we need? We need linear in G gates. And the reasoning is the same as the previous answer, which is that now we can consider how many states can be generated from G gates. In the simplest setting, where the architecture is fixed, and also each of the gate have a constant number of choices, then capital H would just be constant raised to G. So for this problem, it essentially connects back to the previous one, because we can just think of H to be some constant raised to the power G. And hence now, we know from the previous answer, this only requires log H. And hence, here, it will only be linear in G. So that's for the simplest case, when the architecture, kind of like in this unitary circuit U, where the gates are placed, are being fixed. But actually, it doesn't change too much when we allow flexibility in like how we choose things, because the only minor change there would be something like instead of constant raised to the power of G, it becomes something more like constant times polynomial in N, whole thing raised to the power G. And when we take the log of it, it would still be linear in G, but with a log N factor. It's a kind of a small factor we can kind of neglect. So that fixes the problem about the fixed architecture. And then one could also ask, what if the gates are continuous gate set rather than discrete gate set? So there, what one would do is one would consider now doing like a covering net. So the idea of covering net is for each 2-qubit gate, even though there's infinite choices for them, we can kind of discretize them so that we only keep the ones that are, like for things that are too close, we just keep one of them. That's called covering net. And from there, one can also derive things and realize that, oh, actually, linear in G is already sufficient. Just to add on to this question a little bit, but so far, what we talked about is just kind of an upper bound statement. We just say how many measurements is required, what is the best algorithm we can come up with, essentially just utilize that theorem, Clifford. One could also ask a related question, which is, now we realize that, at least for a simpler setting, we need a linear in G number of gates. Is that optimal? Like, can we do better? Basically, in one of our recent paper called Learning Quantum States and Unitaries with Bounded Complexity, we proved that one can also show that linear in G is optimal in the sense that any learning algorithm that try to learn or do tomography of states that can be generated in capital G gates will require a linear number of gates. And hence, using that theorem, we get the best algorithm we could have for this. So now, when you guys were thinking about it, I also added another question. Hopefully, it should also be pretty simple. But this question is about reduced density matrix tomography. So in various cases, after creating the state role, we would like to essentially learn all of the, say, k-qubit or k-body reduced density matrices, RDMs. And note that for, let's say, k equal to 2, even for k equal to 2, there's an n-squared number of reduced density matrices. And in general, there would be roughly order n to the k of them. So the question is, how many measurements do we need in order to learn all the k-qubit reduced density matrices? So again, if you know the answer, feel free to raise your hand and say it.
So I want to say that it's just 4 to the k log n over epsilon squared. And the reason for that is if you just take the n to the k and plug it into the Pauli theorem, you can plug that in for m, and then the k is going to come out, and the factor of k in front of the 4 to the k won't actually affect the big O complexity. Yeah,
That's right. And so there's a little bit of subtlety. In order to learn all the RDMs, for say a subset of k qubits, we should also consider like all possible, say, different Pauli terms within that k qubit. So there's a little bit of blow up on the m side. It's not just order n to the k, but something like order n to the k times like 4 to the k or something like that. But at the end, the answer is the same. So it only requires 4 to the k log n in order to learn all the k-body RDMs, where one could also compare it to the naive strategy of just measuring individual RDMs that would require order nk, which would be exponentially bigger than what one would get from this theorem. So here, so that's great. So now there's another question that I added, which is kind of related to this benchmarking certification question, but we make a restriction even further. So here we assume that we can implement an arbitrary Clifford circuit, but then one could ask, like, what if we don't want to implement arbitrary Clifford circuit because the CNOT gates and the entangling gates can still be quite challenging in actual experimental platforms. What if we wanted to be very greedy and say we only perform single qubit gates? Then how many measurements do we need in order to check this?
Same as before, question one, because it's scaling the same in terms of M.
You mean are you thinking of using the Clifford theorem or the Pauli theorem?
Using the Pauli theorem, but
The Pauli theorem.
in terms of epsilon, it's the same.
The scaling in terms of epsilon is the same, but what about the 4 to the k? Because there's one complication. So note that here we're essentially, in order to reduce back to that, we have to consider like psi to be the observable. Right? And now if psi is a very complicated state that acts on the entire system, then O would be acting on n qubits. And hence that theorem would say it's 4 to the n. So that would be quite bad. But indeed, actually from what I talked about, so first you cannot use Clifford because that requires entangling gate. One can only use the second theorem. And then as noted, if one uses the Pauli theorem, we see that if one just plug that in, we will get something like 4 to the n over epsilon squared, which is exponentially worse compared to when we just use the Clifford theorem, which is just 1 over epsilon squared. So as of now, we don't really have a good tool to answer this question. But one thing didn't realize it's already so late, but I was thinking of diving into a new protocol that can answer this question in a more desirable way. But basically, due to time constraint, I'll just say the conclusion. But essentially, there's another procedure that also uses randomized measurement, but it's slightly different. And here's the kind of brief kind of illustration or high-level overview of that procedure. The procedure is the following. So instead of like previous, we will, like let's say the Pauli theorem, we will apply random single qubit gate on each qubit and then measure them. Now in the new protocol, what we do is we will choose one random qubit, like here. For everything else, we will measure in only the, let's say, the standard basis. But then for that qubit, we will measure in a random Pauli basis. And basically, we're going to use some kind of a post-measurement or kind of, in a way, similar to like this measurement-induced kind of idea, classical shadow, in order to, so we're going to kind of like condition on what's the outcome there, and then try to create a classical shadow for this post-measurement single qubit. But essentially, on the experimental side, all we do is like measure all the qubits in z basis, and for one of the randomly chosen qubit, we will measure in a xyz basis. And then using more complicated analysis, one can show that for almost all quantum state psi, we only need order n squared over epsilon squared number of measurements in order to, actually it's like order n squared over epsilon number of measurements that uses only single qubit gates to do this certification. So that's a recent work that we put out this year, but it can be seen as kind of a more advanced version of the classical shadow framework, which I probably don't really have time to dive into, but just a conclusion. So naively from classical shadow, it would require exponential number because the observables we care about acts on n qubits, so k equal to n. But there's a more clever way to implement it and can be reduced to polynomial in system size. So now for the remaining time, I wanted to use the slide to just showcase a bit on what are some applications that people have considered in using classical shadow, what are some applications of doing this certification using single cube measurements, and then kind of conclude, and I also talked about how classical shadow can be used to like train machine learning algorithms to solve quantum many-body problems, and then conclude with some discussion about quantum advantage and quantum simulations. So, yeah. Thank you. So far, what we have been talking about was this paper, predicting many properties of a quantum system from very few measurements. And that was already 4 years ago. And over the 4 years, there have been tons of progress. People study variants of this procedure and so on. Is there a question?
We improve the bound on the powers, like we allow geometry to
Ah, you mean the randomized Pauli where there's 4 to the k. You're wondering like, what if we allow a little bit of entangling gates, but not too much? So in Clifford circuit, basically that corresponds to a kind of a linear depth quantum circuit. So I guess you're wondering, what if we just apply a little bit of entangling gate, but like maybe the depth is still low, and then what would happen in that case? So actually we I think last month, we put out a paper that proves that actually if one just consider a very shallow one-dimensional Clifford circuit, like a random Clifford circuit of roughly log n depths, we can show that that's actually already enough to essentially get the full Clifford result. So recall that there's 2 theorems. One is Clifford, one is Pauli. Pauli doesn't use any entangling gates. The first one uses a deep circuit. And now one could ask, what if we do these like shallow, few entangling gate circuit? But basically one can prove this that actually a shallow circuit is already as powerful as these deep Clifford circuit.
And can you enforce geometrical boundary like in a brickwork circuit?
Yeah, it's like it's a 1D brickwork or 2D brickwork. It all works. So. Is there more questions? If not, then I'll briefly say a few. I'll quickly go through some of the slides that I prepared. So far we've been looking at this classical shadow formalism, which uses these random unitary to scramble a system and then perform measurements. And in this recent paper, what we prove is that these random unitaries, if we wanted to create these 3 designs that I was talking about, we only need a very shallow circuit, like a 1D geometrically local log depth circuit. It can already form very high constant design. And hence, even with shallow circuit, one can already get the power of these very deep Clifford circuit. And using classical shadow formalism, one can estimate different properties. What we have been seeing was like the quantum fidelity for doing certification. It can also be used to predict nonlinear properties like entanglement entropy. And from the reduced density matrix tomography, or reduced density RDM tomography, we see that it can be used to predict 2-point correlation functions or Hamiltonians, local observables, etc. So there have been a lot of different works on understanding the applications of classical shadow. Here is just one of them in our original paper. In this plot, we're showing like as the probability of error appears, how does the fidelity drop, and how we can use classical shadow to predict fidelity versus like some neural network approaches. So here what we found was like, as you guys have also done through the exercise, using classical shadow, one can accurately predict fidelity and by just applying some random Clifford gates, and it's also rigorous. So when the probability of error increases, the fidelity goes down, and the classical shadow would track that accurately. On the other hand, there have been these popular methods called neural network quantum state tomography. However, sometimes neural network quantum state tomography can hallucinate prediction because it's not guaranteed to predict accurately. At least a priori, when you just train it, it's not guaranteed to do that. And when we just take the software that people have created and apply it to this case, what we found is that it significantly report the fidelity. So the fidelity was as close to like 0.5, but it's still reporting something close to 1. And that could be problematic. But that's one of a downside of having an algorithm that doesn't have rigorous guarantee, is that in many cases, actually, neural network quantum state tomography works very well. Sometimes could be even better than classical shadow, but it lacks rigorous guarantee, and hence sometimes can lead to erroneous prediction like this one. So there have also been various other applications of classical shadow, such as in quantum chemistry simulation. Basically, in a lot of simulation algorithms, like variational quantum circuit, or some more advanced version, like this quantum Monte Carlo-based approach by Bill Huggins, published in Nature in 2022, they require estimating tons of observables from the quantum device in order for the simulation algorithm to work properly. So there they've incorporated this shadow tomography technique. It's like they have some circuit that would generate these like Walker state, and then they utilize shadow tomography to learn and estimate properties and use that to guide the quantum Monte Carlo algorithm that was running on the classical computer in order to solve for ground states. That's another application. But in general, one can think of classical shadow as a universal quantum to classical converter, because when you have some quantum state, we can always do this procedure that we talked about to create some classical representation of this quantum state. And then by looking at that classical representation, one can apply tons of different classical computational techniques, such as using machine learning algorithm to address quantum problems. So I'm going to dive into that a little bit later. So some of the examples include like, given some classical representation of ground state, so that grayish is essentially the classical shadow representation of some quantum system. We can feed it into a classical ML and show that it can accurately classify quantum phases of matter. Another example is by taking data, like we do a bunch of quantum simulation and use classical shadow to turn those output state into a classical representation. Now we can use them to train ML model, such that the ML model have the guarantee that given a new Hamiltonian that we have never seen before, it can accurately predict ground state. So I'm going to talk about that a little bit later, towards the end of this lecture. But now I wanted to dive into this a little bit that I kind of didn't have much time to talk about. But this is a recent paper with John Presco and Mehdi Solomanifer, where we consider the problem of certifying quantum state using few single qubit measurements. So we've seen that when we allow entangling gate and Clifford circuit, then we can certify them efficiently from the question that you guys thought about. But as we have also seen, if we're only restricted to performing single qubit measurement, it seems to be much weaker. But actually in this paper, that was also out this year, we found a variant of the classical shadow protocol that estimates this quantity that we call shadow overlap from single qubit measurement that provides a surrogate to fidelity. So note that in order to measure fidelity, we either need like a deep circuit, like a deep Clifford circuit, or just inverting the state. But here, using single qubit measurement, we can estimate something else called shadow overlap that have the property that if the fidelity is close to 1, then shadow overlap would also be close to 1. But if the fidelity is close to 0, then the shadow overlap would be also far from 1. So it kind of gives like a surrogate for it. And some of the applications of it includes like benchmarking, like using the shadow overlap, we can certify if the state has high fidelity. In the paper, there's more discussion of it, but here are just some numerical experiments comparing this shadow overlap to XCB. So note that XCB is another approach that only uses single qubit measurements, actually just Z-basis measurement to try to do quantum state certification. But note that XCB, because it only measures in the Z basis, it can never be truly accurate. So sometimes it could also fail very miserably. But in this case, this is a well-known setting where there's a hard random state, like target state is a random state, and there's white noise. In this setting, it's well known that XCB works, and shadow overlap also works. very well in tracking the decay of the fidelity. The same also holds for 20-qubit system. But now when we start to consider not white noise, but some say coherent noise, that's also very common in the actual system, then now suddenly XCB start to deviate from the true fidelity. In this case, XCB somehow is reporting a lower fidelity than the true fidelity, or lower value than the true fidelity. On the other hand, shadow overlap captures much more accurately because shadow overlap doesn't only measure in Z basis. It also measures 1 qubit in a random XYZ basis. And what we found was that that's actually very powerful. Here's another situation for a bigger system, 20 qubit. And now things start to change more significantly. In this case, we have, instead of a hard random state, we have a more random structure state, also again subject to white noise. For in this case, XCB still performs well, but the variance is very large. So when you do the same number of measurements using XCB and using shadow overlap, we see that the XCB has a much bigger variance. So sometimes it becomes much noisy. And for 20 qubit, similar, it has much bigger noise. And now if we focus on these random structure state with coherent noise, now XCB really breaks completely. So as the coherent noise starts to increase, the fidelity should go down, but somehow XCB, because it only measures in a Z basis, it cannot really truly see coherent noise, and now it's estimating some crazy number, like it's well above 1. So that's one thing we observed. On the other hand, shadow overlap, while it's not perfect, it tracks the true fidelity much better. And this is another example, but for 20 qubit, we still see that XCB has this problem of estimating or reporting a fidelity that's much higher. And that's, again, a problem with algorithm that's heuristic in nature, because XCB only measures in Z basis, so it cannot really do certification rigorously. So that's one application, but there's also a lot of other applications in using certification, because certification is really as we have seen, if we have certification, then now we can do hypothesis testing, and when we can do hypothesis testing, we can do learning. So we can also utilize this shadow overlap, which is like a variant of classical shadow, for performing neural network tomography. So note that previously when we compare classical shadow with neural network tomography, we see that neural network can report a number that's very wrong. But essentially what a certification algorithm allows us to do is to not only certify that the state created in the lab is close to the desired state, but we can actually do it in the other way. So we have a state in the lab, and now we train, say, a neural network to try to approximate or try to model the state in the lab. And now what we can do is we can certify the neural network, which is with the state in the lab, again, using the same procedure. So by utilizing the certification protocol, it allows us to train and certify ML model. And now when the neural network has been certified, we can show that the prediction from the neural network will be accurate. So essentially give rigorous guarantee to some of these heuristic models. So the training is still heuristic. We don't really know if the ML model is going to train well or not, but after it trained, we can just kind of check it to see whether it's have really learned well or not by running a certification protocol. So that's the second example. There are some plots and stuff, but due to time constraint, I'm just going to skip them. Another example is in optimizing circuits. Say the goal is to prepare a target state psi, and what we wanted to do is we wanted to optimize some circuit so that it produces the desired state psi. But how can we check whether we have prepared the desired state? One way is to essentially do this certification procedure. So we can utilize some measure, like using fidelity, or here using this shadow overlap quantity to try to maximize it, maximize between the state generated in the experimental lab to the one that we actually want. And if it's close to 1, then we know we succeeded. So that's another example, or another application where we can use shadow overlap for. And here are some numerical experiments from our paper. But now, before ending, I wanted to talk about one of our result for utilizing classical shadow to train ML model to solve some hard quantum many-body problems in this paper. But the motivating question in here is that we wanted to understand if classical machines can learn to solve very hard problems in quantum physics. And can they yield better solutions than non-machine learning algorithms? So there have been a lot of excitement about using AI to solve quantum problems. And we would like to better understand that from a rigorous perspective. So one of the kind of a key task that I think people wanted to use quantum computer for is to solve for ground states. So, or here, using a more ML language, we wanted to be able to predict ground state for a given Hamiltonian. So the setting is this. We consider there's a family of Hamiltonians, h of x, that was parameterized by this high-dimensional vector x. So think of x as it's specifying the, say, the laser intensity or the field, like the magnetic field that was applied onto the system, or x describes the few-body interactions, etc. And the goal here is that given a vector x that describes a Hamiltonian h of x, we wanted to predict the ground state for that Hamiltonian. So note that there are tons of quantum algorithms for doing this, like adiabatic quantum algorithms, or cooling algorithms, Gibbs sampling, or phase estimation, etc. There have been a lot of quantum algorithms for designed to this, but here we wanted to focus on using classical algorithms. So one thing to note is that this is well-known. This is a well-known, very hard problem. Even when there's a lot of restriction, like we assume that we only care about 2D Hamiltonian with a constant spectral gap, and the goal is just to predict some one-body observable in the ground state. Even in that setting, we can show that this is like this is very hard. So like assuming that NP-complete problems cannot be solved in randomized polynomial time, one can show that there should not be any randomized classical algorithm that can achieve a good prediction error in polynomial time. I hope these are all well-known statements that finding ground state is just very hard in nature. So one could ask, like, can classical ML algorithm do something useful for this challenging problem, like maybe solving it in certain regimes? So the key difference between a normal classical algorithm and a classical ML algorithm is that classical ML algorithms are require a training set. So for example, here we can consider a setting that we have some parameters or have some Hamiltonian. We try to synthesize or prepare the ground state in the lab, and now we perform these randomized measurements that we talked about to create, say, the classical shadow representation of the ground state. So we kind of go through what we just talked about, but in a more advanced fashion. So what we talked about is there's a single unknown state, and we just try to learn a representation for it. But we can do that for multiple different states corresponding to multiple different Hamiltonians to create an entire training set that can be used to train some classical ML algorithm. So that's the setting that we consider here. So now recall that this problem is known to be very hard, even under a lot of restriction. But what essentially we proved in this paper, as well as a follow-up paper, is that a classical ML algorithm can actually achieve a very small prediction error epsilon using just a logarithmic amount of training data and unlog computational time. And it works for any constant dimensional system, like a 3-dimensional material, or in any constant spectral gap, works for any local observable and any average prediction error. So here is just some basic idea for how the classical ML algorithm work. The result holds for some very big neural network. And the idea was basically that in the training set, we already know the ground state for some of the Hamiltonians. And now what the ML algorithm could do is could try to extrapolate, try to learn the pattern, and try to extrapolate from the training set to the new Hamiltonian. And what we can show is that this can be done efficiently and accurately.
How big was your data set for training?
Yeah, so basically asymptotically, it's like order log n. You can think about it as the following. It's like there's an n-qubit Hamiltonian, and the number of parameter is also roughly order n in the qubit size. And in that situation, one can show that the training data size, like how many Hamiltonians ground state we should already get scales roughly order log n. So not a lot, pretty small. So what this essentially shows is that polynomial time classical ML algorithms trained with data. So note that this data itself can be hard to obtain from classical algorithm. So polynomial time classical ML algorithm trained with data can predict much better than any polynomial time classical algorithm. That's essentially combining this proposition that I briefly mentioned and also this theorem that we proved.
So in the previous lecture, we learned that solving the ground state energy is a QMA hard problem. So how does this like circumvent that limit? Especially if you say it's any spectral gap. So
yeah. That's a great question. So in a way, I also said that, right? Like I said, classical algorithm, it's very hard. And we need to, in order to find ground state, we need to solve NP hard problems. But why am I saying something like, oh, classical ML algorithms suddenly can do it efficiently? And then that's related to this question, like why ML algorithm can be more useful than non-ML algorithms. And the reason is because what the ML algorithm is doing is that it's just, all it has to do is it only needs to generalize from data, which can be much easier than computing everything from scratch. So if you don't have the data, then the problem is extremely hard. But now when you have it, suddenly generalizing from it to a new Hamiltonian kind of within the same family becomes much easier. So that's kind of one way of thinking about this. So another way to think about it is that data can contain computational power. And we have a previous paper about this called Power of Data in Quantum Machine Learning, published a few years ago, where we established this complexity theoretic diagram, where we have the classical algorithm, BPP, sitting here, and we have BQP sitting over there. It contains BPP. But now we have this other strange class, this blue class, corresponding to classical ML algorithms that get access to a training set. And one could show that if the training set is arbitrarily powerful, then it can actually go even outside of BQP. And however, if one assumed that the data just come from quantum experiments, then this blue circle will be, again, within BQP. It's kind of
you want the cube?
Maybe follow up to that question, like if one attempts to like include the complexity cost for generating those data, like can one make a comparison between like the?
Oh yeah. So
does that make sense, or if that's
yeah. So I guess you're wondering like, what if we? So what do you mean complexity for generating?
Like the time cost for generating, like using the best known algorithm.
Aha. You mean like using the best classical algorithm?
Yes.
Yeah. So that's what I was trying to say. Like, if the data is arbitrarily powerful, then it can actually go out and solve some super hard problems. But now we can start restricting the complexity of the data. So for example, we say the data has to be generated from quantum experiments. Then suddenly this blue circle would now be inside BQP. And now if we make the further assumption that the data that the classical ML algorithm learned from can be generated with classical algorithm, then now this blue class collapsed back to BPP.
Yeah. Could you help me to clarify, like, is classical shadow kind of absorbed as part of the architecture of the machine learning model, or is more like just to validate that your machine learning model is properly trained?
Yeah, so classical shadow can be used in various regards. So first, classical shadow is part of the training set of the ML model. So you can think about it as it's an input to the ML model. Part of the input is to train it. And then one can ask, how are we going to utilize the classical shadow representation within the ML model? In this paper, we are using it in a specific way. So the classical ML algorithms is kind of taking some structure of classical shadow when it's using them.
So if I understand correctly, is it kind of like working as some kernel function or descriptor that kind of like encode the data set in a more like structured way so that the
Yes.
machine learning. Okay, so your machine learning architecture is still separated from classical shadow, right?
Yes, yes, it's
So we can assume that if a machine learning model itself is not very expressible, it does not have a good, architecture,
Yeah.
it still won't be able to achieve good accuracy.
They
right?
won't be able to achieve it.
Okay.
There has to be some specific ML algorithm that can really take advantage of the classical shadow data in order for this theorem to
Okay, thank you.
Yeah, maybe I missed it, but what if I have a quantum phase transition in my Hamiltonian?
Yeah. So here, I'm always assuming that, that's a great question. So I'm assuming that maybe around here. We're always considering a smooth family of Hamiltonians with a spectral gap within the class. And hence, there's essentially that assumption says there's no phase transition within them. And it's in that context that the machine learning algorithm can generalize. So as of now, it's not clear if the ML algorithm only trained in one phase, and now you ask it to predict a completely different phase, it will probably fail. So here one should think about it as there's a big phase of matter, and then you only get a few of them, and now the ML algorithm can easily kind of interpolate and extrapolate to feel out the entire space.
I see. And okay, but if I do have a quantum phase transition, I could just train on either side.
Yeah, you could also do that.
And can I then get like arbitrarily close to the phase transition?
So when you're approaching phase transition, then essentially the gaps start to close.
I see. Yeah. Okay.
Yeah. So if you want to look into it, it has a kind of a, if I recall correctly, I think an exponential scaling gap. So as long as the gap is like roughly constant, it's fine. But if it starts to become very close to zero, then things start to blow up.
I see. Thanks.
Oh, yeah. For the tasks that are outside the BQP with machine learning with data, could
You mean,
in this.
Yeah. Actually, in this Power of Data paper, we presented a few kind of contrived examples where one can use classical ML algorithms trained with some data to solve some extremely hard problem. There's ways to encode like some halting-ish, like kind of halting problem type into it. So if the data is like very, very powerful, then it can solve.
Could you give some example of data that are not from quantum experiments?
So that would be more hypothetical because at least I believe that the universe is can all be computed within BQP, and hence one shouldn't be able to get such data. I just meant like formally speaking, if the data can be very powerful, then yes.
Oh, then can we just safely say that in our universe, classical machine learning algorithm is inside the
Yes,
BQP?
that would be how I was thinking about it. Yes.
One more question.
So actually, what's the formal separation between classical algorithm and a classical machine learning algorithm? Like, can I have a classical algorithm such that it can also use data information?
Yeah. So basically, the only separation is really just you can kind of hide this ML. It's just classical algorithm that can kind of adapt itself based on the data that was fed into it. So that's one way to formalize it. But in a way, one can take comparison with this complexity class called advice class, which are essentially algorithms that can take an advice from an all-powerful being. So that's also a well-studied complexity class in complexity theory. And in a way, this blue class is a subclass of the advice class. It's called P/Pauli. So one should think of this blue thing as being contained in this other more powerful P/Pauli class. Because in P/Pauli, the algorithm not just get training data, but it actually gets the most useful advice from an all-powerful being. So that's another class that people have studied, and this blue class actually contained inside that.
Thank you.
Sorry, another question. So you mentioned that basically shadow tomography, it can kind of help like improve the accuracy of classical machine learning model in a sense, right? But I think another very important question for machine learning algorithm is the trainability. Does it also help with that? Because we know like some machine learning model, it can be very expressive and then it can achieve good accuracy or even good, transferability, but it's just so hard to train.
Right. So here, I mean, when I say this, when I say computational time, it also means the computational time for both training and also prediction. And hence, at least the algorithm that we design, it's a pretty simple algorithm that's kind of like kernel-based. But that algorithm has efficient trainability.
Okay. But here you say a classical machine learning algorithm. It seems that this is a very general
when I say
statement.
A classical algorithm, it's the one that we designed in our paper.
Oh, okay. It's not any machine.
It's not
okay.
any. It's not any.
Okay, cool. Good to clarify.
One
Thank
we
you.
designed.
So you mentioned that this algorithm was pretty simple, but can you briefly elaborate on the structure of this algorithm you used to train your model?
Sorry, can you say again?
Could you please briefly elaborate on the algorithm you used to train your model?
Sure. Yeah. So there's a few of them. The original one is different from the improved one, and since the improved one is better, I will just talk about the improved one. But the improved machine learning algorithm, one can think about it as it's kind of a kernel version of a graph neural network. So think about it this way. So here we're always focusing on a finite dimensional quantum system. So there's a geometry that we know of, like it's say a 2D array. And then now what the algorithm would do is it will essentially apply think about it as it's like a neural network that acts on local patches. So it looks at the parameters associated to the Hamiltonian local terms in each patches. So the patch would be kind of overlapping a little bit on different location. Like at different qubit, we just open like a small ball around them, and then the neural network would try to like look at all the parameters within each of them, and then extract like a high-dimensional vector out of them, and at the end use that to make prediction on the ground state properties or the ground state itself. So that's like the rough structure. And what we need to prove is that so first we need to prove that this functional form will be able to be expressive enough to like predict ground state properties accurately, and then also second, like it can be efficiently trained and so on. So that's kind of the general idea. Okay, so now let's jump back, and due to time constraint, I'll skip some of the numerical experiments. Essentially, just TLDR, it just says, oh, ML works well. And also, there's another related theorem that I kind of briefly talked about earlier. Instead of predicting ground state, we can also consider a problem of classifying quantum phases of matter. So now the input is, say, a classical shadow representation of the ground state, and the ML model, the goal of the ML model is to predict which phase it's in. Is it a trivial phase? Is it a topological order phase? Etc. And basically, one can show that with, again, a carefully designed classical ML algorithm, the ML algorithm will be able to learn efficiently, like train efficiently, and predict efficiently, predict the phase accurately. So here's another numerical experiment showcasing that the ML algorithm that we designed actually works. But now before I conclude, I wanted to say a few words about how what we talked about, especially this result on this provably efficient machine learning for quantum many-body problems, relates to quantum advantage in quantum simulation. So now imagine the following story. Suppose that there's some family of Hamiltonians that we care about. This family could correspond to maybe some class of materials that we would really like to understand, like some superconducting things, or some family of chemicals or molecules that we care about. There's some families of Hamiltonian. And now suppose, a priori, we don't really know how to, say, solve the ground state, understand the ground state properties of these Hamiltonians. So we run a ton of extensive quantum simulation using all kinds of tools that people develop in this community to try to solve for ground state, try to solve for thermal state, and try to learn properties, say using classical shadow or using other related learning algorithm to try to learn the output from the simulation, etc. Let's say after doing tons of work, we eventually found an efficient classical algorithm for finding ground states of Hamiltonians in this family. So a priori, we don't know. But now after doing tons of quantum simulation, we found it because we learned from it. And then we learned all the insights from the simulation and learned from it. And then we found an efficient classical algorithm. So now we can ask this. In this case, do we say there's quantum advantage for this Hamiltonian family? In a way, one would, in some sense, it felt like no, because there's an efficient classical algorithm for finding ground state of this Hamiltonian. So it seems like quantum simulators is now defeated by the classical algorithms. This is just a hypothetical story, but I do believe that this story will eventually happen many, many times in the future. And in a way, the theorems that I just talked about already said that this will have to happen, because for any smooth family of n-qubit gap local Hamiltonians, our result proved that there always exists an efficient classical circuit that can accurately predict the ground state of new Hamiltonians. And hence that story, even though I don't think it quite have happened yet, maybe if one talked to Michel Lukin, they would say many-body scar is kind of like this. Like they did tons of simulation experiments using their Rydberg atom systems, and then they discover this new phenomenon called many-body scar, which can also be simulated using efficient classical algorithm. But that doesn't quite work because in a way that a priori the family is already simulatable classically. So, but that's related to this story. So basically, what this result also suggests is that there could be a quantum advantage in discovering, in finding an efficient classical circuit for this family of Hamiltonian. But then once the classical circuit is being found, there's no more quantum advantage. And I do believe that in the situation of quantum simulation, this will happen a lot. Like we use quantum simulator to study Hamiltonians. And after we study for enough times, we now really understand it. And now we can write down an efficient classical algorithm that can solve ground state and estimate properties of that. But then I would say, in a way, there's still quantum advantage, but it's not the standard one that people talked about in complexity theory, because usually the one, in this case, we would say there's no quantum advantage. So what I wanted to conclude was that by combining learning algorithms and quantum simulators, it can potentially offer some useful advantage in discovering new classical methods for solving quantum many-body problems. But there's also an important thing to note is that after the discovery has been made, then there might be no more quantum advantage. But I would say this is still a form of quantum advantage, although it's kind of vague. Like how to really talk about these quantum advantage. Some kind of quantum advantage in discovery is a little bit hard. So I just wanted to kind of pose out there that I feel like combining ideas from learning algorithms and combining ideas from quantum simulation, maybe we can start to formalize and characterize these new kinds of quantum advantage. Maybe we can call them quantum advantage in discovery or quantum advantage in scientific discovery. And I feel that that remains to be a very important open problem. So that's it for my lecture. Thank you so much for listening.
I think we can afford one or two more questions.
One or two more questions? No, I see two hands in front.
I'm curious, do you have any comment on like using quantum systems to solve classical problems, maybe classical analog problems? And yeah, I'm just curious.
Yeah, so we have several results about like quantum advantage in learning from experiments, where essentially it's learning from like quantum experiments or physical experiments. So in a way, that's like quantum advantage in analyzing quantum data. But there's very limited things known about quantum advantage in learning about classical data. I think so far we only know some very contrived example that I wouldn't even count them as example. Like one can just kind of contrively made make like factoring problem into a learning problem and just use Shor algorithm and claim that's like a quantum advantage in learning classical problem, but I don't think that quite counts. So I would say right now it's not clear that there's a very promising quantum advantage in machine learning, especially for learning of classical problems. But I do believe there's hope, and I am currently working on trying to understand if there's something that can be proved in that realm. So, yeah.
Thanks.
One last question.
Maybe regarding this last point, how big are these families that you learn? How big are these families that you learn? You always parameterize them with this X.
Oh, yeah. So
like,
it could
how
be
often
any
would I have to
smooth
find?
family such that within that family, it's the Hamiltonians are all spectrally gapped.
Maybe slightly more practically, like,
Yeah.
can I simulate like a couple molecules and then I can do all of quantum chemistry, or
No. So essentially, like, I think the right physical intuition is that it has to be in the same phase. So the notion about a smooth family of gapped Hamiltonian, one should really understood it as it's like a same phase. So if you have a physical kind of quantum phase of matter, then within the same phase, if you now know a few points, then now you can extrapolate and predict everything else within the same phase. But at least as of now, we don't know how to predict it outside. And to be honest, I think it should not be possible to, if you only learn from one phase and now you can predict all possible other phases. So in the molecule case, I don't know if there's a good notion of molecules and phases, like phases of molecules. I don't know if that's something like that exists. But I would say in that realm, it would be something more like, yeah, there will also be some kind of phase for different molecules. And now when you know a few of them, now for that phase, we know. Like maybe it's a superconducting phase or it's some other phase. But now if you know a few examples, and then the ML algorithm will be able to generalize within that phase. But now if there's a new phase, then the ML algorithm will probably fail. But then the same story might happen again for a different phase. Like we do tons of simulation, and now we gather all these classical data, and now suddenly people can come up with some classical algorithm for solving that phase. And then that story keeps going on. I do believe that might happen a lot of times in the future when we do have good quantum simulators, and probably our community, we're going to say like, oh, we can use this quantum simulator to simulate these things, and maybe after a year or two, like the classical people start looking at our result and then come up with classical algorithm for doing the same phase. I think that will probably happen a lot because of this kind of inherent structure.